Welcome back to the Deep Dive, everybody. Today, we're going deep on something that's, well, it's kind of fundamental to machine learning, but I feel like it doesn't get talked about nearly enough. It's all about, like, can we really trust what our models are telling us? Like, how do we know a prediction is solid, not just, a lucky guess?
You hit the nail on the head there. See, a good prediction and a bad prediction, they can look identical if you're only seeing the final output, the point prediction. And that's where this idea of uncertainty quantification comes into play.
Okay, uncertainty quantification. I've seen that term thrown around. I think I have, like, a vague sense of it, but could you, like, break it down a bit? Why should we care? Make it real for our listeners.
Absolutely. Think of, let's say, fraud detection. Your model flags a transaction. Is it worth investigating right away, or is the model just unsure? Knowing how certain the model is can help prioritize investigations and save everyone time and effort. Or imagine your banking app classifying transactions, right? If it's uncertain about one, it could ask you, hey, is this groceries or eating out? Instead of just guessing wrong. And in demand forecasting, if you know the range of possible outcomes, you can avoid overstocking or running out of inventory. So instead of just a single prediction, you get a better understanding of what might happen.
I'm starting to see the value here. It's like knowing how confident the model is gives so much more information to work with. But, like, where does this uncertainty come from? It's not like the AI is, like, having a crisis of faith, right?
Not quite. But it's not this perfectly deterministic process either. Uncertainty can pop up all over the place. The data itself might have errors. Imagine using house floor type to predict price, but the data is wrong for some houses. Or consider the model training process. Train the same algorithm on slightly different data, you get a different model, different predictions. Plus, some algorithms have randomness built in, like neural networks.
Right, so the data might be a bit fuzzy, and the learning process itself can introduce some variation. What else contributes to this uncertainty?
Well, think about it. Smaller data sets naturally lead to more uncertainty, and we make decisions during model building, like tuning hyperparameters, which can lead to slightly different results. And what about missing values in the data? Those create uncertainty too. Even in tasks like image classification, where things seem straightforward, we can have uncertainty. What if different human labelers disagree on an image? The model learns from a noisy target. And some models, like decision trees, can be super sensitive to small changes in the data, changing drastically with just a few data points difference.
Yeah, I see that. Like a cat dressed up as a dog, even we might be unsure. And if the model's not sure, we want to know about it. So we have these potential issues, but many models output things that look like uncertainty, right? Like probabilities or confidence scores. Can't we just use those?
You would think so, right? But it's not always that simple. A model might say 90% chance it's a cat, but these probabilities are often poorly calibrated. In a well-calibrated model, when it says 90%, it should be right 90% of the time. But that's often not the case. Bayesian methods make assumptions about the data distribution which might not hold up in practice. And bootstrapping, while useful, can underestimate the true uncertainty, especially with limited data, giving us a false sense of confidence.
So just taking those outputs at face value, what the source calls the naive approach, can lead us astray. We don't have any real guarantee about how well they'll generalize to new data.
Exactly, we need something more robust. And that's where conformal prediction comes in. It takes those uncertainty scores, whatever they are, and gives us rigorous, probabilistic guarantees about how often we'll capture the true outcome.
Okay, conformal prediction? That sounds promising. Tell me more. What are the key advantages here?
First and foremost, you get that guaranteed coverage. You can say, with 95% confidence, the true value is within this range. Second, it's surprisingly easy to use in many cases. You don't need some fancy new algorithm. It works with any machine learning model. It's model agnostic. It doesn't make assumptions about your data distribution. You don't even need to retrain your model. And the best part, it works for various tasks. Classification, regression, time series, you name it.
So instead of a single point prediction, we get, what, like a range of possible values?
Yeah, exactly. For classification, it gives you a prediction set, a set of likely classes. For regression, you get a prediction interval, a range where the true value likely falls.
That sounds incredibly practical. Is there anything we need to be aware of? Any caveats?
There is one key assumption: exchangeability. Basically, the data we use to calibrate our conformal predictor, to set up those guarantees, needs to be similar to the new data we want to make predictions on. If they come from very different distributions, the guarantees weaken. Like time series data where order matters, you need special adaptations to handle that.
Okay, exchangeability. Makes sense. Our setup data needs to reflect the kind of data we'll see in the real world. Now, the source dives into a specific example, classifying beans. What's the story there?
Picture this. A bean company, they've got a naive Bayes model classifying beans into, say, 7 different varieties, but customers are complaining about mixed bags. Not all the beans are the same type. So they want to guarantee that, say, a bag labeled Seeker actually has at least 95% Seeker beans.
A reasonable business goal. How did they approach this initially, using what we call the naive approach?
They looked at the probabilities from their naive Bayes model. They thought, okay, if the model says there's a 95% probability or higher that a bean is Seeker, let's put it in the Seeker bag.
And did that work? Did they get their 95% guarantee?
Not quite. When they tested this on new beans, the bags labeled Seeker only had the correct variety about 89.6% of the time. So those probabilities, while seemingly intuitive, didn't translate into the guarantee they needed.
Okay, so just relying on the raw probabilities wasn't enough. What was the next step? Is this where conformal classification comes in?
Exactly. The data scientist realized she needed a different approach. Instead of trusting those probabilities directly, she decided to create prediction sets. Each bean would have a set of possible varieties associated with it, with the goal of ensuring that the true variety was in that set at least 95% of the time. And to do this, she used the model's probabilities, but in a different way, to calculate what's called a non-conformity score.
Non-conformity score. What is that exactly? How does it help us?
For each bean, the score was 1 minus the model's probability for the correct bean variety. Let's say the true type was Seeker, and the model assigned a probability of, say, 0.9 to Seeker. The nonconformity score would be 1.9, which is 0.1. So the score essentially measures how surprising the actual outcome was to the model. A low score means the model was very confident. A high score means it was more unsure.
Okay, so we have this score that reflects the model's uncertainty. How did she use it to get that 95% guarantee?
She had a separate set of data that the model hadn't seen during training. This is super important, called the calibration data. She calculated the nonconformity score for each bean in this calibration set. Then she did something interesting. She sorted these scores from lowest to highest. To achieve a 95% guarantee, meaning a 5% error rate, or alpha of 0.05, she found the score that corresponded to the n plus 1 alpha nth quantile of these sorted scores, where n is the number of calibration examples. This quantile becomes our threshold.
I see. So this threshold is like a cutoff point. If a new bean score is below this threshold, we're confident enough to include it in the prediction set.
You got it. Now, for a new bean, she would get the model's predicted probabilities for all the bean varieties. For each variety, she'd calculate the nonconformity score. The prediction set for this new bean would then include all the varieties whose score was below that threshold we got from the calibration data.
So a new bean might be predicted as, say, just Durmason or maybe Durmason Seeker if both of those scores were below the threshold.
Precisely. And the key is, on average, across many new beans, the true variety will be in these prediction sets 95% of the time. That's our guarantee.
Yeah, the source talks about a Python library called MAPE. How does that fit into all of this?
MAPE, which stands for Model Agnostic Prediction Interval Estimator, makes implementing conformal prediction much easier. You don't have to do all those calculations manually. They have this MAPE classifier. You wrap your existing model with it, provide the calibration data, and then when you call predict on new data, you get both the original model's prediction and the conformal prediction sets.
So in our bean scenario, she could have plugged her naive Bayes model into MAPE classifier, used those calibration beans to fit it, and then got the sets for new beans.
Exactly. And in MAPE, you can set the coverage level, like our 95% or alpha 0.05. It handles that threshold calculation and gives you the output nicely, telling you which classes are in the conformal set.
And the source also mentions analyzing the size of these prediction sets. Why is that important? Like, why not just always include all possible classes and be super safe?
Well, we want our predictions to be informative, right? A prediction set containing every single bean variety isn't very helpful, even if it's guaranteed to be right. Ideally, we want smaller sets that still provide good coverage. And MAPE helps you track this. In the bean example, the sets were mostly of size 1 or 2, which is pretty good.
And I imagine that alpha parameter we talked about, the coverage level, plays a role here. A lower alpha, meaning higher coverage, would probably lead to bigger sets.
Absolutely. If you want to be more certain of capturing the true class, you need to cast a wider net, so to speak. There's a trade-off between coverage and the size of the sets. And MAPI lets you experiment with different alpha values to see how that trade-off looks for your problem.
Gotcha. So it's not just about achieving high coverage, but also making sure our predictions are still useful and actionable. But the source then hints that the bean company's celebration might be a bit premature. Something about marginal coverage. Could you explain that?
Right. This is an important point. That 95% guarantee, the one we've been talking about, is a marginal guarantee. It means that across all the new beans we classify, 95% of our prediction sets will contain the true variety. But it doesn't guarantee that for each individual bean variety, the coverage will be 95%. Some varieties might have lower coverage, others might have higher, as long as the overall average is 95%.
Ah, okay. That's a subtle but important distinction. So if the company specifically wanted to guarantee that their seeker bags were 95% pure, just having that overall average coverage isn't enough. They need something more like class conditional coverage, where the guarantee holds for each specific class.
Exactly. And the basic score method, while great for marginal coverage, isn't very adaptable to how easy or difficult it is to classify different bean varieties. Some beans might be easy to classify, others might be trickier, and the score method doesn't adjust for that.
All right, so the score method has its limitations.
Yeah.
The source then circles back to the cat-dog classifier to explain the intuition behind conformal prediction a bit more visually. Could you walk us through that?
Imagine we have our cat-dog classifier, and we've got our calibration data. For each image in our calibration set, we calculate the nonconformity score, like 1 minus the probability of the true class, right? So now we have a measure of how surprising each image was for the model to classify. Then we sort these calibration images from the most certain, the ones the model found easy, to the most uncertain, the ones where the model was less sure.
So we're ranking the calibration images based on how much the model struggled with them.
Exactly. Now, let's say we want 90% coverage, meaning we allow for a 10% error rate, so alpha is 0.1. We find the threshold in our sorted scores such that 90% of the calibration images have a score below it and 10% have a score above it. This threshold basically divides our calibration data into two regions, a certain region and an uncertain region. And the key idea is that we're using the distribution of uncertainty in our calibration data to define what we consider certain enough for new unseen images.
And it's super important to use this separate calibration data, not the training data. Right?
Absolutely. Models tend to be overconfident on the data they've already seen. If we use the training data, we'd likely set the threshold too low, thinking our model is more accurate than it is. That would lead to bad coverage on new images.
I see. We need that unbiased view of the model's uncertainty. Now, when we're setting this threshold based on the nonconformity scores, are we only considering the true class labels? What about the model's predictions for the wrong classes?
That's a sharp observation. It might seem like we're only looking at how well the model predicts the true class. And you're right, conformal classification mainly controls for the coverage of those true labels. But we also care about not including too many incorrect classes in our prediction sets. If we didn't care, we could just say every image is both a cat and a dog and get 100% coverage, which wouldn't be very useful. So while we set the threshold based on the nonconformity scores of the true labels, we also evaluate how small our prediction sets are on average. Smaller sets with the same coverage are better.
So it's a balancing act. We want to capture the true label, but we also want our predictions to be as specific as possible. Now, once we have that threshold, how do we actually make a prediction for a new image?
For a new image, we get the model's predicted probabilities for all the possible classes, cat, dog, whatever they are. For each class, we calculate the nonconformity score, which is 1 minus the probability of that class. Then, any class whose nonconformity score is below our threshold gets included in the prediction set. Those above the threshold are deemed too uncertain and are left out.
So we might end up with a prediction set that's like cat, lion, if both of those scores were below the threshold, indicating the model thinks those are both plausible options.
Exactly. We get a set of possible outcomes based on the model's confidence. The source then neatly summarizes this whole process as a recipe for conformal prediction.
Right, they talk about training, calibration, and prediction.
Training your model, as usual. Calibration involves computing those nonconformity scores on your calibration data, sorting them, picking your desired confidence level, or alpha, and finding the corresponding quantile to use as your threshold. For prediction, you compute those scores for new data points and include any classes or values below the threshold in your prediction set or interval.
And they emphasize that the choice of nonconformity score is a key differentiator between different conformal prediction algorithms.
That's right. Different scores can lead to different types of prediction regions with different properties. The basic approach we've been discussing is called split or inductive conformal prediction, where we split our data once. But There are also fancier techniques that use resampling to calibrate the predictor.
The source briefly touches on transductive CP. Could you elaborate on that?
Sure, transductive conformal prediction is a bit more involved. It uses the actual test point you're trying to predict on as part of the calibration process. So you're kind of tailoring the prediction region to that specific point. This often means you have to refit your model multiple times, which can be computationally expensive, especially with large data sets, but it can sometimes give slightly better results than the inductive methods.
They also compare single split, leave one out, and cross-validation for calibration. What are the trade-offs there?
Single split, like what we described, is the simplest and fastest, but it can be a bit unstable because your calibration set is fixed. Leave one out, or LOO is at the other extreme. It's computationally intensive because you're essentially leaving out each data point in turn and recalibrating, but it can give you slightly tighter prediction regions. Cross-validation, or CV, is kind of a middle ground. You split the data multiple times and get an average calibration. And MAPE lets you easily switch between these different approaches.
Okay, so there's a whole world of options for calibration. After this, the source talks about interpreting the prediction regions and what that coverage guarantee actually means.
Right. For classification, our prediction region is a set of classes. For regression, it's an interval. The key thing to remember about, say, a 90% coverage guarantee is that it's a statement about the long-run average. It means that if we make many predictions, on average, 90% of our prediction regions will actually contain the true outcome. But it doesn't guarantee that any single prediction is correct with 90% probability. This is similar to the idea of confidence intervals in statistics. It's a frequentist interpretation of probability.
That's an important distinction. The source then connects conformal prediction to the overall supervised learning mindset, emphasizing the importance of evaluation.
Exactly. Just like we need a separate test set to evaluate our model's performance, conformal prediction needs that separate calibration set to establish the guarantees. It's all about making sure our model generalizes well to unseen data.
The discussion then dives deeper into conformal prediction for classification, revisiting the bean example and introducing some useful functions from MAPE.
Right. They talk about classification coverage score and classification mean width score. The coverage score simply tells us what percentage of our prediction sets actually contain the true class. The mean width score tells us the average size of our prediction sets, how many classes are in them on average.
And they reevaluate the naive method, just using the probabilities directly, on the bean data. Unsurprisingly, the coverage is too low, around 90%, instead of the desired 95%. This really drives home the point that uncalibrated probabilities are not reliable for guarantees.
Exactly. The model was overconfident in its predictions.
Then they apply the score method we discussed earlier using MAPE. They get good coverage, around 96%, but the average set size is 1.8. So on average, each bean is assigned to almost two varieties.
Yes, and this highlights the difference between marginal and conditional coverage, which we talked about earlier. Marginal coverage is the overall average. Conditional coverage means the guarantee holds for specific subsets of the data, like for each individual bean variety. And for the bean company, they really need that conditional coverage to guarantee the purity of their bags.
Looking at the class-wise performance of the score method, they see that some varieties, like Barbanouaya, only have 92.5% coverage, while others, like Bombay, have 100%. This shows that the guarantee isn't uniform across all classes.
Right. Some classes might be inherently easier to classify. Bombay, for example, might have distinct features that make it easy for the model to identify, so it always predicts it correctly with high confidence. But that can lead to larger prediction sets, even if they only contain one element. Harder classes, like Barbanouaya, might be more easily confused with others, resulting in lower coverage.
So if we need those per-class guarantees, the score method isn't ideal. This leads to adaptive prediction sets, or APS, which aims for conditional coverage. How does it work?
APS uses a slightly different nonconformity score. Instead of just using 1 minus the probability of the true class, it calculates what's called a cumulative probability score. You take the probabilities of all the classes, sort them from highest to lowest, and then sum up the probabilities starting from the most likely class until you include the true class. So it's not just about how confident the model is in the true class, but also about how much probability mass is concentrated around the true class.
And the calibration process is similar. We find a threshold based on these scores, but the prediction step is different, right?
Yes. For a new instance, we get the probabilities, sort them, and start adding classes to the prediction set, beginning with the most probable until the cumulative probability exceeds our threshold. There's a bit of nuance in how we handle that last class that pushes us over the threshold. We can include it, exclude it, or randomly choose whether to include it.
They test APS and MAPA, trying out those different options. They find that the randomized option gives good marginal coverage, but the sets can still be quite large.
Yes, that's one of the trade-offs with APS. It aims for better conditional coverage, but that can sometimes come at the cost of larger, less informative prediction sets.
They then introduce regularized APS, or RAPS, as a way to get smaller sets. How does that work?
RAPS is a modification of APS. It adds a penalty term to the score for including too many classes in the prediction set, especially those with low probabilities. The idea is to encourage the algorithm to focus on the most likely classes. RAPS has some tuning parameters that usually require using a small part of the calibration data to optimize.
Applying RAPS to the bean data, they find a slightly smaller average set size. But the source notes that RAPS is more useful when you have many classes.
That's right. When you have lots of classes, especially a long tail of classes with low probabilities, RAPS can really help in making the prediction sets more manageable.
Next up is group-balanced conformal prediction. What's the main idea there?
Imagine you want to guarantee coverage not just overall, but for specific groups within your data. Maybe you want to ensure 95% coverage for, say, small beans, and 95% coverage for large beans separately. Group-balanced conformal prediction does this by essentially performing conformal predictions separately for each group. So you have a separate calibration set and threshold for each group. The main requirement is that you need to know which group a new instance belongs to at prediction time.
They illustrate this with the bean example, using the area feature of the beans to define a group of small beans and applying conformal prediction to that subset.
Yes, showing how you can adapt the method to specific needs.
And finally, they talk about class-conditional APS, or CCAPS, as a way to get per-class coverage guarantees without needing to know the class beforehand.
Right. CCAPS is a clever technique. You train a separate conformal predictor for each class using the calibration data. So for each class, you have a separate nonconformity score and threshold. Then, for a new instance, you calculate the score for each class using its respective predictor. The prediction set is the union of all the classes for which the score is below its threshold. This guarantees coverage for each individual class, but it can lead to larger overall prediction sets because you're essentially accounting for the most difficult class to predict.
So there's a whole toolbox of methods for conformal classification. Choosing the right one depends on whether we need those conditional guarantees and what kind of properties we want our prediction sets to have.
Exactly. It's all about finding the right trade-off for your specific problem. Now let's switch gears and talk about regression. In regression, instead of predicting a class, we want to predict a numerical value. And instead of prediction sets, we want prediction intervals, ranges where we're confident the true value will fall.
The source mentions quantile regression as a way to get intervals. What's the limitation there?
Quantile regression is great. It lets you predict different quantiles of the target variable's distribution, but it doesn't give you any guarantees about coverage. It doesn't tell you how often the true value will actually fall within those intervals.
So we need to bring in conformal prediction again. And the source outlines two main strategies for conformal regression.
Right. We have conformalized mean regression, where you start with a regular regression model, one that predicts the average value, and then use conformal prediction to build an interval around that prediction. And then there's conformalized quantile regression, or CQR, where you start with quantile regression and conformalize the interval between two predicted quantiles.
Let's start with conformalized mean regression. How does that work in MAP?
It's actually quite straightforward. You have your regression model, like a random forest or a linear regression. You wrap it with MAP's MAP regressor, provide the calibration data, and specify the desired coverage level. MAPI calculates the nonconformity scores, which in this case are typically just the absolute residuals, the differences between the model's predictions and the true values in the calibration data. It uses these scores to determine a fixed width for the prediction intervals. Then, for a new data point, it takes the model's prediction and creates an interval of that width around it.
The source walks through an example using rent data and a random forest. They generate prediction intervals, note that they all have the same width, and then evaluate the coverage.
Yeah, and they find decent coverage. But one of the limitations of basic conformal mean regression is that the intervals are not adaptive. They have the same width, regardless of the input features.
So to get adaptive intervals, we need something more sophisticated.
Exactly. One way is to use cross-validation or leave one out during calibration. This introduces some variation in the interval widths. And there are more advanced, locally adaptive methods that try to estimate the variance of the residuals locally and adjust the interval width accordingly.
Okay, so conformal mean regression is a good starting point, but achieving adaptivity requires more complex approaches. Now, what about conformalized quantile regression, or CQR?
CQR is a really interesting approach. You start with two quantile regression models, one predicting a lower quantile, say the 25th percentile, and another predicting an upper quantile, say the 75th percentile. So you get an initial interval between these two predictions. Then you apply conformal prediction to this interval to guarantee the desired coverage.
And what's the nonconformity score used in CQR?
It's the maximum of two values, the difference between the lower quantile prediction and the true value, and the difference between the true value and the upper quantile prediction. So it's measuring how much the true value falls outside the initially predicted interval.
I see. And how is the threshold used during prediction?
You get the lower and upper quantile predictions for a new data point. Then you adjust this interval by subtracting the threshold from the lower bound and adding it to the upper bound. This widened interval has the desired marginal coverage guarantee. And CQR can be adaptive because the quantile regression models themselves can produce intervals of varying widths depending on the input features.
They implement CQR in MAPI, noting that it requires three models, one for the lower quantile, one for the upper quantile, and one for the median. They get a warning about potential overlap between the quantiles, which is something to watch out for. The resulting intervals have different widths, demonstrating that adaptivity, and they evaluate the coverage.
Yeah, and they find good coverage. CQR is a powerful technique for getting adaptive prediction intervals in regression. It can potentially give you tighter intervals than beta-conformal regression, but it does require training multiple models and can sometimes have issues with quantile overlap, especially if the models are not well calibrated.
So we've covered a lot of ground with conformal prediction for classification and regression. But the source also emphasizes that conformal prediction has much broader applicability.
Absolutely. Conformal prediction can be applied to various tasks like time series forecasting, multi-label classification, outlier detection, and even probability calibration. It's a very versatile framework.
They mention some specific methods available in MAPI, like NNBPI for time series, CRC and RCPS for multi-label classification, and using outlier detection scores for, well, outlier detection.
Right. And the beauty of conformal prediction is that it's not tied to any specific algorithm. You can use it with any model that provides some measure of uncertainty or confidence.
It's amazing to see how this seemingly simple idea of using nonconformity scores in calibration can be applied to so many different problems. This has been a truly insightful deep dive into conformal prediction. I think it's clear that going beyond point predictions and quantifying uncertainty with guarantees is crucial for building reliable and trustworthy machine learning systems. Thanks for walking us through all of this.
It's been my pleasure. As you continue your learning, think about how these ideas can be applied to your own work. There's so much potential here for making machine learning more robust and interpretable.
And to our listeners, if you're interested in learning more, I highly encourage you to check out the resources mentioned in the show notes. Until next time, keep diving deep.